Que nuestro invitado habla en inglés, entonces vamos a pasarnos a este idioma. Good afternoon, everyone. We have a great guest this afternoon. His name is Samuel Birch, and he's a research fellow at the Department of Earth, Atmospheric and Planetary Science at the Massachusetts Institute of Technology. His research focuses on understanding the evolution of the surfaces of planets, moons, and small bodies, and deciphering what these first surfaces tell us about their past. This is done using both spacecraft observations of planetary surface and numerical simulations. Currently, his research focuses on both the evolution of the polar landscapes of Titan, Saturn's largest moon, and the surface of Comet 67P, and I can pronounce the other one. So, welcome, Sam. We're really happy to have you here.
Thank you. Very happy to be here. Alrighty. I guess I can share my screen and hop right in.
Sure, please.
Alrighty. Oh.
There it goes.
Can everyone see my screen?
We see it perfectly.
Alrighty. Well, thank you for having me. I'm excited to be here. I'm going to be talking about Titan, my favorite place in the solar system, other than the Earth. I really quite like the Earth, but Titan is quite an amazing little world in and of itself. So I always like to start, I saw this, Linda Spilker, who was on Cassini, showed this once, and it really blew my mind. And Titan is a moon, and it orbits Saturn. And I didn't quite understand what Saturn was or what a giant planet truly was. And then she showed this graphic. So this is the Earth and the moon to scale, and this is Saturn. And Saturn and its rings fit perfectly inside of the distance between the Earth and our own moon. And Saturn really, truly is a giant planet. And Titan orbits it at a distance that's 9 times farther than our moon orbits our Earth. So if you lived, say, hypothetically in the cloud tops of Saturn and you looked up, Titan would just be this little yellow dot deep on the horizon going around you every 16 and a half days. Now, Titan is not small by any sense. This is our moon above the Golden Gate Bridge. I just took this photo from the internet. And if you imagine Titan somehow was replacing our moon, this is what it would look like in the night sky. And with its atmosphere, it's almost twice as big as our own moon. And because it's twice as reflective, you're getting a lot more light. So if you imagined walking around at night on a full Titan moon evening, it would actually be quite bright and you could walk around quite easily. So Titan is this big, massive world, and it would be a planet. It just happens to orbit Saturn instead. Makes it no less interesting though. Okay. Titan's also unique in that it's what we call an ocean world. So what is that? It's a lot of these moons, and including Ceres in the outer solar system, they are covered, their crust, if you will. Here on Earth, it's silicate rocks. So when you walk around, you're picking up dirt and stuff like that. That's silicates. On Titan, it's water ice. And below that, its mantle is liquid water. It's an ocean of water that's quite massive below it. And then below that, depending on how big you are, you have molten cores or iron cores or silicate cores like you do here on Titan. And Ganymede and Europa and Enceladus, they're all these ocean worlds that could be these big habitable places deep below their surfaces. Titan's the only one, though, that has this big puffy atmosphere above it. So it also intersects here with Venus, Earth, and Mars, in that it's an atmosphere world. So it is a unique destination for us to go explore. So this evening, I'm going to walk you through both how did we explore Titan and where did we get to where we are today. Then I'll take you through the atmosphere and then down to my favorite, the surface. So I always like to start back at the beginning. Titan was discovered by Cassini way long ago, over 300 years. Christian Huygens, this is a picture of his notebook. And you can see Moon 1 here, if you can see my pointer. He's counting the hours in each day of which it's orbiting this yellow dot orbiting Saturn. And Moon 1 ended up being called Titan. And there's also Moon 2, 3, 4, and 5, the other moons of Saturn as well. About 300 years later, if I jump way ahead, Gerard Kuiper measured the spectra of Titan, and he saw that there's methane absorption. And the only way you can get that is through an atmosphere. And that made it really interesting because it's this big moon, but it also has an atmosphere. It's the only one like it. And you might remember Kuiper because there's also the Kuiper belt, which is named after him, way out in the outer solar system. And then in 1979, Pioneer 11 flew by Titan, and that kind of solidified Titan as this ultimate destination that we have to go explore. So Voyager 1 and 2, which were twin spacecraft in the 80s, and they were meant to go fly by Jupiter, then Saturn, then Uranus, then Neptune together in this grand tour of the solar system. And Titan was so interesting that they essentially took a left turn with Voyager 1, and they had to take it out of the plane of the solar system. So they couldn't continue their journey to Uranus and Neptune, but they decided it was so interesting that they had to divert the spacecraft to go see Titan. And what did they see? So with the cameras, they didn't see much of anything at all other than this big orange ball here on the right. It has this thick atmosphere full of hazes that I'll get to in a moment that obscures or blocks all the light from getting off of the surface. So we can't see anything with our eyes, but they sent radio waves through the atmosphere. And with that, they can measure the temperature and pressure all the way down. And what it showed is that methane and ethane, natural gas, if you will, are both stable as liquids, kind of like water is here on Earth at the surface. And there was predictions that maybe there's an ocean's worth of ethane covering the whole surface. So it's this icy moon covered by a liquid ethane ocean with this thick atmosphere, maybe. So they pointed the big Arecibo telescope in Puerto Rico, and they expected to get these returns of liquid ocean. And they didn't quite get that, and it wasn't consistent with that. So then they revised the estimate, saying maybe it's this frothy ocean that's kind of full of suspended foam, if you will, or that there's isolated seas and lakes. And that ended up to be kind of prophetic later on, and that is kind of what we saw, just not in how they expected it. And then this, we decided when the Hubble Space Telescope was up, we pointed the most powerful telescope we had at Titan, and these are images that you can see rotating on the right of Titan's surface as seen by Hubble. And there's a couple fuzzy blobs, and most of it is dark, and there's this one bright spot. And they hypothesize here in this paper, here's a quote, most of it is dark. There are some bright features, and they wondered what that might be. And in green, these are the things that ended up being exactly right. And it's amazing that this data in the 1996, well before Cassini with a telescope up above Earth's atmosphere could get data like this, and they can make answers that were actually quite predictive 30 years later. So Cassini was designed as a collaboration between the European Space Agency and NASA. So NASA was to build Cassini here on the right that you can see, and there's people here for scale. And this big white thing on the top is the radar, which both communicates with Earth, but it's also how we see Titan's surface. And what it does is it sends down a radio signal that bounces off the surface, comes back to this big receiver, and then we can create an image later on from those signals. That's the main way that we see through this atmosphere, because again, in the visible, it's completely blocked out. And then Huygens was built by ESA, and this was a probe that was to get dropped off to Titan's surface. So Cassini and Huygens were designed to go explore Saturn, Saturn's rings, and Titan, and stop off and check out the moons as well. And Cassini launched in 1997, got there 7 years later in 2004, and it had a 5-year prime mission. So on the bottom left is all of Cassini's orbits around Saturn, And what it did is every time it flew out, each orbit, most orbits, it would leverage Titan to shape and sculpt its orbit and change. You can see the tilt of the plane of the orbit. And each different color is the spacecraft was healthy, so they extended the mission until they ran out of fuel, and they decided to go fly between Saturn and the rings there in red during the grand finale. And in total, we got 127 views of Titan, different flybys. Initially, we only planned 3 flybys of Enceladus, but it ended up being an amazing little world in and of itself. And with these geysers coming out of this ocean, so we flew by it 20 more times later in the mission. And you can see there's lots of stats here, but the ones that strike my eye are 500,000 images and almost a terabyte's worth of data. It's a remarkable mission with multiple spacecrafts, thousands and thousands of people were all part of this, and it was an amazing team. So back to our Hubble Space Telescope image of Titan that you can see here. And the way to look at this is the equator is flat across the middle of my screen, and then the North Pole and South Pole are at the top and the bottom. And it's just like a normal map, if you will. And this is that big bright spot. And Cassini filled it in. About 74% of it was covered by this radar instrument. And that's what these strips are. And you can see here that this bright spot is these mountains that we see. This dark material here are sand dunes that wrap all the way around the equator. And up at the poles, as I'll get to, is where your liquids are. And you'll ask, why are there all these strips? And that's the kind of the necessity with the way that we observe Titan, is that we weren't orbiting Titan, we were orbiting Saturn. And when we flew by Titan, you would get these little strips of imaging every once in a while, every flyby, and you build that up and build that up into this big patchwork of images. So that's the background. That's where we were. That's our data of Titan. So what about its atmosphere? So comparing Earth on the right and Titan on the left, this is a nice graphic from Ralph Lorenz and Christophe Sautin. And they show, you can see on Earth, we have big, tall mountains about 10 kilometers compared to a Titan, which is quite flat for most of it. Your highest mountain is about 2 kilometers tall. And then your clouds are kind of restricted. So if you ever look at clouds here on Earth, they rise up and then they kind of get streaked across. And whenever you look at clouds, you see this streak at the top. They kind of hit the top. They have this cap, if you will. Whereas on Titan, you have both methane and ethane clouds, and they form at different temperatures. So they freeze out at different temperatures. So they're at different elevations. So you have 2 cloud elevations, but if you look, they're much higher than on Earth, almost 3 times higher. And then Titan also has these haze layers. And these haze layers are what make it difficult to see. And they extend up to 650 kilometers, which is, if you imagine parachuting through Titan's atmosphere, that's where you start to feel the atmosphere. Whereas at Earth, it's at least 10 times lower. So Titan has this big, thick atmosphere that extends far higher than you get here on Earth. It also has weather and seasons, and I say just like Earth. So it has this circulation, we call them Hadley cells on Earth, and where you have warm evaporation at the equator, and you get clouds kind of at these predictable latitudes of 60 degrees north, the equator, and also at 60 degrees south. And they move around a little bit depending on your season, but they're generally, we have 3 set cells, if you will, on Earth. On Titan, it's colder. This atmosphere, again, is big and dense, 4 times denser than our own atmosphere. And it's also cold. There's not that much energy. So it has 1 Hadley cell that moves in southern summer. It rains a lot, and there's lots of clouds at the southern hemisphere, like this cloud here. And then at the spring, your Hadley cell or your rain moves to the equator, your clouds. And then in the north, in the summer, you get clouds there. So essentially the clouds track and follow the summer. It's very almost predictable way, if you could say. And it has lots of clouds. So that on the previous slide was just one example. This is from Paul Corley's, who looks at Titan's clouds a lot. And you can see there are these wispy clouds. You maybe don't get the big, thick cumulus storm clouds, if you will, or hurricanes and stuff like that. partly because, again, you don't have the energy, the sunlight to drive these processes, but you do get quite a lot of clouds. And you typically find them at Titan's poles. And what this means is, unlike the Earth, where it's humid and rains the most at the equator, on Titan, your tropics, if you will, are up by the poles, and your equator is this desert, and it's very dry. And the most important part of Titan's atmosphere, you might think, gotcha. The most important part of Titan's atmosphere is the photochemistry, or chemistry driven by photodissociation, or photons coming from the sun. So, or high energy particles, if you will. So this is Titan here on the left, and you see these strips around it. These are these haze layers. And what's going on is methane in the atmosphere is broken up by these high energy particles. They kick off, this is methane, carbon and 4 hydrogens. You kick off a hydrogen, and these other parts can then recombine into all sorts of other things like ethane or other organic molecules and hazes. So that's what creates these hazes, is you're breaking up methane and it's recombining into all these other things, and then these things fall out to the surface, whereas your hydrogen is lost. It's this light particle that just goes off into space. So over about 10 to 100 million years, or the lifetime of about the dinosaurs, your methane is lost in Titan's atmosphere. But throughout that time, it's making all these organics. Your methane is interacting like a liquid on the surface, and this stuff is falling down to the surface as a sediment that then gets reconfigured by all sorts of different processes. So there must be something, either continuously or once in a while, it essentially burps a bunch of methane and then it gets depleted, and we happen to catch Titan at one of those times where it has an atmosphere. But what's interesting is the chemistry going on with all this organic production and stuff is a lot like what the early Earth was, where you didn't quite have your oxygen yet, but early life kind of fed on this, and then you had biotic life that produced the oxygen in our atmosphere that we now know. So Titan is kind of like a laboratory where we can go study our early Earth. And it's really interesting. What happened? What is the chemistry that happened on early Earth that gave rise to life on Earth? Well, that is, some of it could be happening today on Titan in its atmosphere and on its surface. Okay, so down to the surface. These are the first views of Titan in 2004, and I can imagine they started planning the mission, if I remember, in 1989, and they finally got there 15 years later, and this is the images you got. It must have been absolutely spectacular. You can see some rivers here and some big sediment, and for reference, I was just a kid up in Canada hoping to be an NHL hockey player, and I never had heard of Titan, but it truly speaks to the longevity and how hard it is to go explore a place in the outer solar system like Titan. And anyone, just some random kid from Canada, can even go explore Titan, not knowing when it was first there that the world even existed. And this mission, they welcomed people in, and it's a perfect example of how to run a mission, in that it's generations and it takes a team to go explore a world like Titan. At the equator, Titan has dunes, sand dunes, if you will. It's a big desert. And if you look at comparable dunes on Earth, this is in the Namib Desert in Namibia, and this is on Titan. And these are big piles of sand that have wrapped all the way around the entirety of Titan's equator. And for scale, this is a handheld camera from a drone, and you can see this sand piling up in these long strips on Earth. And you can imagine Titan's equator as like the Sahara Desert, but it wraps all the way around. So it's this huge dune field. It also has some impact craters. So if you study impact craters, it's not the best spot to go generally, because on the moon or something, if your body is old and it doesn't resurface itself because of active geology, it just accumulates craters. So that's what we see on the moon and on Mars somewhat. On Titan, it's more like Earth in that it's actively getting eroded and reshaped and buried. So it doesn't have a lot of craters, which to me makes it interesting. But if you do study craters, there is a great opportunity too, because you can imagine when your impact hits the surface, it creates this nice warm little pond in this bowl-shaped hole in the ground. And then if you have these organics, you can imagine that the chemistry going on in that warm little pond could be analogous to the chemistry going on in our early Earth. And I'll get back to that at the very end of why that's so interesting. It also might have volcanism. So this is work by Rosalie Lopez, and this is Doom Mons on the right, named after Tolkien's Mount Doom. And then this is Sotra Patera, a 2-kilometer mountain right next to a 1.5-kilometer hole in the ground. And as my former boss, Alex Hayes, likes to say, it goes boom from the hole and then plop on the mountain. And this is also interesting, again, because you have water instead of on Earth where you melt the crust and then you have lava coming out. On Titan, if you melt the crust, the lava is liquid water, and that then would ooze onto the surface and freeze in a process perhaps analogous to how volcanoes work here on Earth. With Huygens, as it descended through the atmosphere, it saw these rivers immediately. So this white thing that you see here is a high standing, a plateau, if you will, and it's cut by these rivers. And then these dunes, you can actually see them in the background. That's what these 2 long strips are. Those are the dunes. And as Huygens descended, if we zoom in, it saw this beautiful channel network that if you didn't tell me it was Titan, I would think that this is something on Earth. It's really quite remarkable from the first images that we get, detailed of Titan's surface. Boom, it's this. It's really exciting. This is another view of all the images now stitched together. This is that plateau. This is where those rivers are here, where my mouse is. And you can see the dunes off in the top right. And Huygens, the probe, landed right here, where this red square is, where my mouse is. And if we zoom in, it saw this gravel, if you will, these rounded cobbles sitting on the surface. And for scale, this is a soccer ball, so it's big, 10-centimeter size rounded cobbles. So other than how big they are, this is something that you might expect to see in a gravel river here on Earth. But with big particles instead, perhaps. And this is a really enticing thing because first thing you see when you land is something so familiar. I mean, Titan it is amazing. Okay. The other thing Huygens saw is methane. It detected it right at the surface. And the theory behind that is that the probe, when it was flying through the atmosphere, got really hot. When it landed on the surface, it landed on this cold surface. And you can imagine if you walk around on a swampy day right after it rains and the ground is a bit squishy and water's coming out, you can imagine if a hot probe hits that, the water's going to evaporate. Well, perhaps the same thing happened on Titan, and methane was instead the thing that evaporated. And it saw it right as it got to the surface. So it's an amazing detection. When we looked with Cassini, with the radar throughout the rest of Titan, we saw rivers everywhere. And these are not small rivers. These would be some of the biggest rivers on the Earth as well. These are huge rivers, and anything that's dark like this in the rest of the images are liquids. So these are liquid-filled channels, whereas these are bright, and we think that they're probably more like desert rivers that you would see, lots of gravel like what I showed you earlier, but they're huge rivers that you see all across Titan. We look at some of the rivers like the one I showed you on the previous slide, and some of them are deeply incised. They're like canyons. And the way that we got this measurement is as Cassini was flying by, it sent a signal down, and then that signal came back to Cassini. And it's kind of like a bat with its sonar in a way, and you can measure the distance. And when they did that, they saw these deep gorges that the rivers seemed to be located in. And that was really exciting. It's almost like a canyon that these rivers are flowing through, and maybe it cut it itself. And then when we looked at the power, it said that they had to be liquid filled. And the connection there that's so exciting is that you have liquid filled channels at different elevations, and they're connected. And that has to mean that there's active flow on Titan's surface today. So you can imagine sitting in this gorge, looking up, and there's water trickling in all around you, and you could actually hear it better than you could hear it on Earth because the atmosphere is so dense, so sound waves travel quite well. So it would be an amazing spot to go have a picnic on a boat in this deep canyon. It would be quite an unbelievable sight, and sounds. And it also has rain. So we caught it in the act a couple times, and this is one example. And you can see that the surface was bright, and then a big cloud came over and it darkened it and got really wet for a while, and then it evaporated away. We saw this happen a couple times, but it's more confirmation that this methane is active and changing the surface today. We also found lakes. So the prediction that there was lakes on Titan was true. They just happened to be at the poles. We didn't think that the tropics would be at the poles, and that's what these dark features are. And when you look at down on the poles, both of the poles, the North Pole on the left and the South Pole on the right, and for reference, it takes a bit getting used to looking at these types of maps, but this would be the Earth if you looked at it the same way. You're looking straight down on the pole. So you have Russia on the left and Canada and Greenland here on the right. And when you look, all the lakes and seas on Titan are on the North Pole, and you have 4 or 5 on the South Pole. So all the liquids are at the poles, and almost all of them are at the north. And what we think is going on is it's climate cycles driven by changes in Titan's orbit. So just like changes in Earth's orbit lead to glacial cycles, where you go in and out of ice ages, on Titan it's similar because Saturn's orbit is changing. And Titan follows whatever Saturn does. Saturn is the boss, if you will. And over these 300,000 years, methane cycles from pole to pole. So it currently is the wet time at the North Pole and it's dry at the South. So, and I showed you on the previous slides that it has lakes and seas, and we kind of like to classify things in geologists. So I'll start with the lakes. They come in lots of different flavors. We have filled lakes here, the dark ones, and then ones with the same shapes, but they're bright. We think that those are empty. Some of them have these halos around them, and then others, they look like they're eating into each other, kind of like chicken pox, if you will, that's spreading across. And you can see these lakes kind of just eating into each other as they go back. Some lakes are drying up actively. So in 2011, there was a paper that talked about lakes that disappeared with the radar. And then there was a recent paper by Shannon McKenzie who showed a very similar type process with different instruments. But you can see in green, she highlighted it's nice and dark, so we think these were liquids. And then we saw them with different instruments in the infrared. And in the infrared, lakes are this dark blue-green color, and it's very much not liquid anymore. And we think that the liquid either evaporated or went down into the subsurface. And it's more evidence that it's changing, it's this active world. They also have what we call evaporites around them. And you can see on the image on the right, you have some filled lakes up on the top of the image and some empty lakes on the bottom. And when we look at the infrared and map that on top, you have this red material. And this red material we think is evaporite. That what happens is when your lake, it has salt, if you will, Titan salt, whatever that might be, in the liquid, and just like salt in water. And then if you evaporate the water or the methane, the salt is left behind. And this is Devil's Golf Course here on Death Valley. It's the same thing. This lake dried up and left behind this salty sediment. And that's what we think the red material is surrounding these lakes in these images. Lakes also seem connected, connected through the subsurface, that is. And it's a bit of a complicated story, but you see filled lakes next to empty lakes, and the empty lakes are high up. So you can imagine on this drawing here on Earth that the empty lakes are up here on the drainage divide, if you will, and the filled lakes are down here. And they get filled or emptied depending on where the water table is, or on Titan, I guess it would be a methane table. And we think that there's this large groundwater, ground methane system that's communicating between the lakes. And what is groundwater? Well, if it's a big rainy day and you go outside and you see a cliff face or just a hill and water's coming out after the rain is all gone, that's your groundwater. And this is just a picture of water oozing out of the surface. This is groundwater. It's what most of us drink. It's what the world relies on for fresh water. And Titan seems to have it too. Most lakes also have these sharp edges, and they are uniquely Titanian, if you will. There's nothing like it else on Earth or anywhere else in the solar system. And they seem to be these agglomerations. And you would say maybe it's this dissolution because you have this dissolved stuff in the liquid. So maybe you're just kind of eating away at the surface, melting it almost, if you will. We got some topography, again, through this kind of sonar type method, the altimetry mode of the radar. And what it saw are these big raised rims surrounding the perimeter of most of the lake. Well, in this, we only had a couple chances, but it was like, oh, this is really weird. This is this big, tall mountain surrounding all the lakes. That's not normal. And then the one on the bottom, we saw it again of a filled lake. This is a Winnipeg locust, the one that I was lucky enough to name. And it also had these rims. So what we did is we said, okay, can we see them around other lakes? And when we looked, they seemed to be everywhere. And when you zoom in, you can see this big mountain, hundreds of meters tall, that surrounds most lakes. So we don't really understand what's going on. We have all sorts of ideas, and we brainstormed every possible way you can make a lake, and nothing seems to work. And we're kind of stuck in a puzzle. It'd be really great to know, because there's hundreds of these lakes that cover the poles. They are a very common feature, and yet there's this big piece of the puzzle that we're just not understanding. I wish I had an answer for you. I just don't. Science is hard sometimes. Titan also has seas, so we classify, they're bigger, these massive bodies. And when I say massive, this is Costa Rica to scale with Ligeia Mare. It is a huge sea. And you can see here on the left is a real image, well, a SAR image, and then the false color is here on the right. And you see straight shorelines. Maybe this is a beach. You see these big rivers draining into it, and it's very dark. So this is a liquid-filled sea that is quite enormous. And it's only the second biggest one on Titan. There's Kraken Mare, here the biggest one in orange, that would be the biggest lake or sea in the solar system that we know of. It's bigger than the biggest lake on Earth, which is the Caspian Sea, by quite a large margin. And in blue, these are a fun graphic that we put together of Earth's 12 biggest lakes, and on Titan in orange are its 12 biggest lakes. And these are huge features that cover massive chunks of Titan's poles. Around the perimeters, it looks like the shorelines, the seas have drowned the topography. And this is more evidence that you're essentially filling up, overfilling, if you will, at the North Pole. But at the South Pole, everything's empty. All the liquids have moved north, and you're flooding the shorelines everywhere. It's like a really bad flood everywhere. And you can see this river is actually flowing through, but it's completely covered by liquid that's completely swamped everything. But whenever you look at their perimeters, there's never any sediment. And whenever you look at a river on Earth, most of the time, when it hits the sea, you see what's called a delta. And this is the end of the Mississippi River in Louisiana in the United States. And it's quite large. This is 20 kilometers across. And there's actually like whole settlements of where people live down here that you can't even see in the image. So these huge features that are millions of people on the Earth live on, and they're always there, or most of the time. On Titan, they're almost never there. So there's a big question of, okay, what's going on? We can do some very simple calculations, and they should be there, you would think, if you're very conservative. But every time you look, there's nothing. And if we keep looking, every time as we scan around the perimeter of the sea, there's never any deposits, except for one time in the southern hemisphere. It is quite remarkable the lack of the sediment at the end of rivers when they hit the sea. So something's going on. They're also connected. So if I zoom in at the connection, the three biggest seas are all connected. If I zoom in, you can see there's a clear river channel that goes between them. And then if I zoom into the other connection, there's another big river channel. And if you were other than a T-Rex, I think you'd be able to canoe between these. It might take you a while because it's many kilometers, but there's a direct connection. So the liquids are sloshing and the seas are sharing their fluids. And one of the more remarkable measurements by Cassini was, again, in this altimetry mode, is it actually measured sea level on Titan. So just like you measure sea level on Earth, there is this surface of liquid on Titan that forms sea level, and Cassini actually measured it. It's really, really exciting and impressive measurement. With those same measurements to measure the sea surface, we also measured the depth. And on Earth, you can do this by using sound waves in a boat, and the sound waves go down to the sea floor, and then they come back, and you can measure the depth. On Titan, we use the radar signal, and what you see here is the first return is the signal comes down, hits the surface, comes back. But the signal also continues into the liquid and it bounces off the seafloor and comes back. And that's what the second peak is. And we've measured the depth of all the seas. And for some of them, you can make even depth maps. And Cassini did this not with a boat and a nice, easier measurement. Cassini was going many kilometers per second, 1,000 kilometers above the surface, flying by, and it made this amazing measurement of the depth of a sea. And it's in a series of works here that I put at the bottom that have described this really cool method. And we also did this to the lakes. So this is Winnipeg Locust again. And when we measure their depths, they're all hundreds of meters deep and they're all methane rich. All that ethane that should be there that everyone predicted seems to be missing. Where it is, maybe it's deeper down in the groundwater, but truly it's another one of Titan's mysteries. They're also really flat. So when we look at water, the seas, the oceans on Earth in radar, you can see land. This is Nantucket Island here, and the sea is very rough with waves because of an incoming storm. On Titan, for the longest time, whenever we looked at them, they were completely flat and dark, except for this one. This is my favorite feature on all of Titan. We've imaged this spot 10 times, which is more than any other spot. And we thought, oh, maybe it's noise, but it shows up every time at the exact same spot. So this is this lonely little island out in the middle of the sea that's otherwise completely flat. And then in 2016, Titan's Magic Islands appeared, and then they reappeared again later. And when I say Magic Islands, they are neither magic nor islands, but we saw in this yellow box that you can see here on the right, here's a sequence of images, and the T is the Titan flyby. So lower numbers is when we first started observing, and we saw nothing, it was dark, and then all of a sudden, these little streaks appeared every once in a while, right here. And we were excited. It's like, maybe this is waves. So this is some really nice work by Jason Hofgardner, who talked a lot about this, is maybe it's waves. It seems to be the most common occurrence on Earth. Waves happen a lot of time on Earth, and the fluid is actually less viscous or more slippery on Titan. Methane is. So it's easy to make waves. They should be there. Maybe this is what it is. But Titan is really cool, and methane does not behave like water necessarily, and maybe they're bubbles. So why do I say that? Well, there's some recent experiments done by Kendra Farnsworth that show if you take methane, and it's not just pure methane, but it's methane with nitrogen in it. Just like water has air in it, there's nitrogen in methane's fluid. And if you change the temperature a little bit, or you add a little bit of methane, all of a sudden bubbles explode out of the liquid. And it is a violent process. Even in some of her experiments, the whole camera got knocked right off. And with the different liquids, it's not just water like it is on Earth, but there's methane, ethane, and nitrogen in the fluid. And these are some experiments here as well, that you actually have two different fluids here. And you can have, if you absorb a bit of nitrogen, you get denser, and you can have a bubble actually descend through another liquid into the liquid in the bottom. So the behavior of methane is very funky and weird. And bubbles can be a very decent explanation as well for those magic islands. Maybe bubbles are very common on Titan seas. And what this means is, when you imagine your methane river is going to be cold, and when it comes into a warm methane sea, you can have all sorts of weird and interesting processes going on. Maybe you have bubbling, maybe you have what are turbidity currents, like you see here in this lab experiment. On Earth, this is with water and actual sand, but it's these deep currents that go all the way down. So you can imagine, and you can even see it in some of the data, if we look and stretch the images really hard, you actually see rivers that go on the left. The river actually goes into the sea, out of the sea, and then into the sea. Rivers on Earth do not do that ever. And then some of these, the river just continues for a very long distance all the way into the sea. So if you're a dense, cold methane river, you might just go into the sea and not even realize you hit the sea and just keep going. So what happens where these fluids mix is brand new research that a lot of people are working on. And it's really exciting because it is uniquely Titan yet again. So where are we now? So I can list what we do know. So Titan has weather, active weather. Today it's raining somewhere on Titan, probably right now. You see rivers of all sorts of shapes, similar to what we see on Earth, sometimes different. They're all over the moon. Some of them are these deep canyons, but it seems to be missing its sediment. So something's going on. There's something we're missing about Titan. The lakes, they only occupy 1% of the surface, and they have a volume of 70,000 cubic kilometers, which is a hard number to conceptualize, but the takeaway is it's a lot of methane, but most of it is actually in Titan's atmosphere, and a very small amount of it is on Titan's surface, and it's all restricted at the poles, today mainly at the North Pole. When we look at these lakes, they are these mysterious features. They have these rims. We don't see rivers going into them. Maybe there's some dissolution eating away at the surface, but we really don't know. We're completely puzzled by how they form. They also seem to be connected by this large groundwater network where the lakes are communicating with each other depending on where they are in their elevation. Are they high up or low down? And then how much rain there is locally. And they're active today. We've seen them change a couple times throughout Cassini. The seas themselves are massive. We can measure sea level. Because of the interesting fluids, you have multiple fluids that you can get really interesting processes, and maybe you can learn something about what's happening on Earth. I mean, we have one data point here on Earth. It's water moving sediment. On Titan, you have all sorts of different processes. They're also really deep, but all the ethane's missing, and they're very active. And I would say it really is unlike any other world. It is Earth-like, but it really is Titan-like as well. What do we not know? Well, we don't know a lot, to be honest. We don't know the composition of the surface really at all. We know that there should be certain things, but we've had a very difficult time detecting them confidently. We don't really know how you make sediment, how you move it, or how you deposit it. Where does it all go? All that stuff coming from the atmosphere, where does it all go? And from that, we don't know how old the surface is. So is this methane coming out once in a while from the interior? How is it there? Or is it always getting supplied somehow? And you always have weather and methane moving around on the surface. And then where is all that ethane? It's got to be somewhere. These are big unknowns that remain. And then regarding the lakes and the weather, how do they form? How big is this groundwater system? What's actually going on those shorelines? What more can we learn? A question that's interesting to me is if it is Earth-like in some aspects, can we learn something about our own planet? Can we actually use Titan to help us out here on Earth? And then in terms of all these organics, where do they go? And when it rains, how often? And how big are these storms? How big can a rainstorm get on Titan? And all of this, or a good chunk of these things, can be answered in the very near future. There is a new and exciting mission getting sent to Titan in about 15 years called Dragonfly. And it's a quadcopter that it'll land at the equator, and its goal is to go explore a crater where some of this water might have been in contact with organics, but it's going to see dunes, it's going to see rivers, it's going to see sediment. It's going to really change our understanding of Titan. And it takes a very long time to get there and to develop these missions, but we are going, and we couldn't be more excited to do so. And with that, I will take any questions that people have. Thank you so much for having me. It was a lot of fun. I always like talking about Titan, and hopefully this was fun for you all too. So thank you.
Sam, thanks so much. It was amazing. Like, yeah, I can't even tell. It was so cool. So we have a lot of questions right now, and we can start by Daniel Francisco, and his question is, why is Titan so appealing to launch a human base for deep space exploration?
Oof, that is a good question. I don't know if I would ever go to Titan. It's 200 degrees below Celsius. it is a great place to go explore, and it's a very easy place to land on. And that's because of this big atmosphere. My former boss likes to call it the pillow of the outer solar system. So it's, as you hit it, it just slows you down, and it's really easy relatively, to land on Titan's surface. And there's also, I mean, you can imagine there's lots of resources. I don't know if it's a place to go make a permanent settlement. I have a lot of other places that I would rather go to, just because it's cold, and like, imagine Antarctica, but then 10 times as cold. It's really miserable, generally. It's an amazing place. The landscapes would be beautiful. Temperature, unbearable.
I can imagine. Yeah, definitely. So we have a question from Genesis Rodriguez. Is there the possibility that Titan begins to work like a crib of life? Like having life without working as a planet does?
So we think that Titan, it probably doesn't have life on its surface today, life like we know it, where water is incorporated. It's just too cold. If you do, it could be in some of these melt ponds at the bottom of a crater, where some of the early chemistry happened. And we don't know how life came out of just stuff getting squished together in the right place at the right time. There's a step from like molecules and stuff to life that we haven't understood yet. And some of that stuff is happening on Titan. So that's why we want to go explore it. There have been theories that there could be completely methane-based life that would not be anything like we know at the shorelines, and a great place where there's lots of energy because there's drying and wetting of the surface. So there could be the energy for life there. And then of course, Titan is just like Europa and Enceladus, and everybody likes to go hope to explore there because it has an ocean, right? Well, Titan does too, and it's actually bigger. And it also has all these organics, natural organics just produced like crazy in the atmosphere coming down. So it's a great place. It's subsurface ocean, I would say, is the best place to go look in our solar system for life. It's really hard to get there, unlike Enceladus and Europa, but it could be easily habitable, just like the other ocean worlds that we know of. Titan could be different mixes of things, yeah.
Great. So we have, this is an amazing talk. Thanks a lot, Sam. What are some actual exploration science opportunities we should pursue for missions to Titan? Mineral extraction, planetary science, weather models, permanent colonies for some reason, or a base for future outer solar system missions, an orbiting telescope for further exploration of Saturn, the outer solar system, and other opportunities that would be better observed from there than from Earth, and exploration of Earths from distance, perhaps to tune our techniques to detect planets and our signs of life and other planets. Oh, this is a really good question.
Yeah, that's a fantastic question. I will answer, I think, part 3 first. We did actually test our technique on how we look for life on exoplanets with, I think, the Voyager spacecraft, though I might be wrong. It was Carl Sagan's experiment to turn one of these spacecraft back and look at Earth to look for what's called the red edge of vegetation. And you saw it as if Earth was an exoplanet, obviously with better signal. But that is an experiment that people have done successfully, and it's one nice technique. Of course, you can always do it better. In terms of looking at Titan, it has everything happening on Earth, and everything happening on all these icy worlds. There's so much to explore. There's weather, of course. You can learn more about how weather works on some of these places and how they interact with the surface. You can learn all sorts of different geology and apply that back to Earth. All the tectonics that you would need to understand to go to Europa is all there. Titan's kind of this wonderful grab bag for all of us planetary scientists to go explore. It has something for literally everybody to go explore. In terms of what we should do, we are sending a helicopter, the quadcopter Dragonfly, back or to Titan, and that has a specific mission to go explore this crater. There's proposals to send a submarine to go into some of these seas. And what's nice about a submarine, you can imagine on Earth, you have to surface to send your radio signals back. That's why submarines surface, because water absorbs the radio waves. On Titan, the methane doesn't. So your submarine can just sit down there and talk to Earth for free. It's really cool. And then there's also orbiters. We barely really know anything about Titan. There's so much to learn on a global scale. And we've really only seen the largest of the large features over 3/4 of the moon. And if you can imagine looking at Earth like that, there would be so many questions and you would just want to go back. And we keep wanting to do that. So I think some sort of orbiter and another lander, there is something for everyone. And there's lots of creative people coming up with lots of creative ideas to go explore.
That's amazing. So is there any evidence of a supervolcano on Titan?
I don't think so, mainly because it's very hard for cryovolcanism to work as it is. So on Earth, volcanism happens because your magma is less dense, so it rises up, and then if you have gas buildup, you can blow it up. And that's kind of how you're in a very simplistic way. On Titan, when you melt the crust, water is actually more dense than ice, right? If you have an ice cube in a cup and you try pushing it to the bottom, it always pops back up to the top. So if you melt the Titan's crust, it actually goes down, not up. So how you do cryovolcanism is a big question. There's certain ways that you can do it and get creative, but it is still a very difficult process. But we see these features, so there's got to be a way. It's probably not explosive though, because it'll be more like the Hawaii volcanoes, that it'll just ooze out. It'll be this very viscous fluid, and you won't get the big gas buildup that can cause a supervolcano.
Cool. So you mentioned one can predict clouds on Earth should be found at around 60-degree latitudes, both south and north. How to reach such prediction?
Yeah, so that's just due to the way that the Earth spins and where it receives its energy. It has moist air rising at the equator because it's hottest there, but you also have moist air rising at plus and minus 60 degrees, partly because of how the Earth spins and how it receives light. And it's a complicated system of feedbacks, but it makes this very predictable pattern. You also have cold air descending at 30 degrees plus north and south. And it's not a coincidence that cold air is dry, so you don't get a lot of rain. And whenever you see deserts on Earth, like the Sahara or southwest US, northern Mexico, or the Namib Sea in Namibia, they're all at 30 degrees south or north. And that's also because of this large scale circulation of Earth's atmosphere. Good question.
What could possibly explain why Titan's equator is a desert?
It's the same thing. So that's a great lead on for this question. Methane condenses at the coldest parts of Titan. It's stable there. It wants to be there. So it does rain at Titan's equator. In fact, the biggest storm we saw was at Titan's equator. It's not very often. And it essentially, you can think the way Titan's climate works is the biggest rainstorms happen very once in a while. The energy is just not there to drive evaporation, which then causes rain. So you build up because the atmosphere is so dense, and then you release and you dry out the atmosphere, and it takes a very long time. Whereas at the poles, you get this not constant, but more frequent drizzle, if you will. And that's what some of the climate models are telling us, that it's this dry desert at the equator that once in a while, when it rains, it really rains. And then it's kind of much more humid at the poles, mainly because it's colder and methane wants to be there.
Is there an explanation of Titan's rapid departure from Saturn?
Rapid departure. We think Titan formed, so the way that you form planets around the sun, so you have a disk, and then you condense rocks and build it up, and you condense rocks, and then you agglomerate, you grab on gas at the end. And whether you do that is whether you're a giant planet or a rocky planet, it's of first order. around Saturn, Saturn formed and it had its own disk, and Titan probably condensed out of that. That's also how we think Jupiter's moons all formed, is that there's this disk and material condensed. So it's like a little mini solar system Saturn is. And that's probably how we think Titan formed, is out in that disk, distant from Saturn. They were never together, they probably.
That's really cool. We have, what is the role of Saturn cosine tidal effects on Titan?
Good question. Very good question. That's a hard question. So the way that tides work is that the closer you are, the stronger the tides generally, and it falls off very quickly, and they get weaker very quickly. So Earth, it has tides driven by the moon, and when the moon was closer, the tides were stronger, and then that caused the moon to drift away over time. Titan is 9 times farther from Saturn than the Earth is from the moon, but Saturn is much bigger. So the tides are still there, but they're just weaker than here on Earth. And the tides cause the seas, circulation in the seas. So they're all connected and they're swapping fluids. And there's some nice work by Ralph Lorenz, who's talked a lot about this, of essentially mixing of fluids due to tides. They're also causing, Titan has this ocean, and then it has an ice shell, and this ice shell is flexing throughout time, and that's causing changes in energy. And there's lots of other complications, but the tides are very important on Titan, and not quite maybe as much on Earth, but they do drive processes.
That's really cool. So have NASA or ESA ever recorded atmospheric phenomena such as thunderstorms or hurricanes on Titan?
Thankfully not, though it would have been really cool. We don't think thunder can happen and lightning on Titan because the way that it happens on Earth is mainly because the polar nature of water. The molecule is essentially, it's a complicated series of feedbacks, but it happens with water because it's a polar molecule, whereas methane is not. And we don't think that lightning is maybe possible. In terms of hurricanes, hurricanes are driven by warm water and circulation, and it takes a lot of energy to drive a hurricane. That's why they don't occur that often, thankfully, but they like warm water and lots of energy. Saturn and Titan, for that matter, are 10 times farther from the sun than the Earth, so they receive 100 times less energy from the sun. And then the atmosphere itself is very thick and it's very insulating. So I think a cold day at night on winter is 91 Kelvin, and then a warm day in summer at the equator is like 93 Kelvin. So it's pretty much the same temperature everywhere all the time because this atmosphere is very insulating. So the ability to drive a hurricane is very difficult. I mean, the ability to make a cloud it's still difficult. It happens all the time. It's just easier on Earth because it has more energy.
That's really interesting. I know Titan's magnetic field is so weak, but have someone done a measurement about Aurora Borealis, or have HST take a picture that looked like that?
So we've seen it on Ganymede, which is slightly larger than Titan, and that's Jupiter's moon. And it has its own internal magnetic field. We haven't detected, to my knowledge, a magnetic field induced like a natural one to Titan itself. And this is probably because its core is just rock. It doesn't have a molten iron component to drive that. Saturn does have a very strong magnetic field, and Titan goes in and out of it depending on where it is in its orbit. But we haven't seen anything like, we did see auroras on Ganymede from Hubble, but we've never seen that on Titan because it doesn't have its own internal field. It just kind of is protected by Saturn's most of the time.
And our last question is, what science experiments are going to be performed on Titan in the next mission? Do you think we could find life on those rivers or lakes?
So I am not on Dragonfly, and I'm not entirely familiar with all its instruments. I know it has a few instruments to sense the composition of the sands, to look for some of these prebiotic processes that led to life. It has a scoop to pick up stuff and put in some of its ovens that it has, I think. I'm not entirely sure. I might be misspeaking. It also has a seismometer on its legs, so it can actually measure Titan quakes generated by tides from Saturn. And then perhaps we can detect the depth to the ocean and the core and things like that. Dragonfly is looking for these prebiotic signatures to life, probably not life itself. What you would see sailing up one of these rivers would be the most spectacular sight I can imagine. It would be kind of like the Grand Canyon, smaller, but imagine like going up a canyon with these rocks all exposed along you. Is there life in the rivers themselves? I can only speculate, probably not, but it might be that weird Titan life in the seas. There's more and more that we're learning about the nature of Titan's fluids, mainly from these experiments. These experiments are amazing. And there's these bubbles and all these different dynamics that, I mean, who knows, to be honest, maybe some of that weird Titan life that people have speculated. If it's going to be anywhere, it's going to be along the shorelines of the seas, which are going to be these dynamic, exciting places. Good question.
If I might throw one in here, please. There's a lake named after you, Sam.
After Winnipeg.
Titan. Yeah, well, can you tell us the story? Sam is from Winnipeg. That's a pretty neat detail. Can you tell us a little bit about that, please?
Yeah, so we were writing a paper about rims, these weird rims that you see, and it was hard to, I kept calling it the seahorse lake because it looks like a seahorse, and that doesn't kind of work well in professional papers. So anyone can name any feature on Titan. All the lakes are named after lakes on Earth, and there's an IAU website that it looks a lot like that, yeah. I can share the link with you, Bruce, that you can name. There's hundreds of lakes and only a few dozen have ever been named. Generally, they're named because somebody's studying that and they need a name for it. So it kind of looks like Lake Winnipeg, and we proposed it and they accepted it, and I was pretty excited. But yeah, all it is that it kind of has to look like the lake, and anyone can name anything.
Well, on Mars, there's Yellowknife and a few other Canadian little landmarks there.
I think there's also Winnipeg on Mars, if I remember. I don't know if this was like storytelling or if this is real, but it was the year that the rover was at this place in January when it was the polar vortex. And for the high in Winnipeg in that January was colder than the high on Mars. And they named it Winnipeg Mars for that reason. It was warmer on Mars than in Winnipeg. I don't know if that's actually true. I like to think it is because it's a fun story about Winnipeg. Winnipeg's really cold.
I would have liked, I don't know, the lake named Seahorse. It's a super cool name.
Yeah, so the IAU, International Astronomical Union, is in charge of the names of things. So all the mountains are mountains in Lord of the Rings books. All like the plains are named after the worlds in the Dune novels. They have prescribed, all the seas are sea monsters. So there's Kraken Mare, which is the Kraken. So as long as you fit in the box, anyone can name anything.
Thanks for that.
Yep.
Thanks a lot for your story. So we have 2 books to raffle. We have New Winnipeg here, and they're asking. We have another question. I don't know if you want to take it.
The New Winnipeg? I mean, it's a little warmer in Winnipeg, I guess. It's not saying much.
Okay.
There's also another question about Enceladus.
Yeah. If you want to answer, it's a really good one. I liked it.
In terms of detecting, so if there's life in the oceans, which we don't know, there's all the right stuff for it that we think that life needs. Whether it happens or not, we don't know what drives it. Enceladus has this big plume coming out, and Cassini actually flew through it a bunch of times to sample it. And there's mission concepts to go do that. And they're going to propose again to go fly by and collect some of this material. Titan's ocean is about 100 kilometers thick or of ice before you get to the ocean. So our crust for scale, I think, is 10 kilometers on the ocean floor. So it's 10 times thicker than our oceanic crust. So you'd be drilling for a very, very long time. And I think there's a big expedition to drill to Earth's mantle, and we still haven't done that. So drilling to Titan's mantle 10 times farther, at 10 times farther from the sun, that's a big undertaking. So it's getting to the ocean is the hard part. Maybe this stuff comes back up when it gets erupted. That's where you would go look. But actually sampling the ocean, Enceladus is throwing out free samples at you. So that's the place to go.
Well, it was really interesting. I think we all enjoyed like everything. It was super exciting. It was, yeah, I didn't know that much stuff, and it's really cool how tides like they work and everything. I think we all enjoyed it. So thanks a lot.
If I could throw one last one at you, I know with these exotic missions, they take decades literally to conceive, then to get funded, hopefully, if that's the case, right? And so the Europa people are working on their side, and the Titan people are, but the case can be made clearly that it's easier to access the oceans, or the water and Titan, even though Saturn's a bit further away. The cost effectiveness, if you were making a hard decision as an administrator, which one would give you the best return for if you were competing in that way?
I'm very biased, so I would say Titan in a way. But I think the other thing that Titan has going for it is that it has something for everyone there. If you study atmospheres, any sort of process there's something for you. If you study geophysics, there's something for you. Chemistry, geology, life in the oceans and these processes, everything that's happening on Europa pretty much is happening on Titan. But then there's way more stuff also happening. It's kind of like if you took Europa and Mars and squished them together, that's kind of, and then it was active today. That's kind of what Titan is. So it's a very interesting place that we've just barely started to explore. If I had to choose one, that would be the one. I would choose all of them if I could. But these missions do, I mean, they take decades because you write your proposal and then you compete and then you work on your proposal and then you're still competing, and it's like a 4-year process that you're putting all your energy into, and then maybe you get picked, and then it's another like 10 years to build your spacecraft and then another 10 years to get out there. So it is a generational undertaking, that's for sure. It takes a whole team, and when you do these things and you conceive them, I mean, you're doing it for the next generation, not necessarily your own. Because there's a whole nother crop of scientists coming behind you. And Cassini realized that, and it was an amazing team to be on, because you're drawing on the experience from all these people, and they're so welcoming. And I think that's how all spacecraft teams should work, because the data is for everyone, it's not for you. And it's really exciting to see. When you see stuff come in, it's a whole new world.
Titan certainly has captured the imagination of many people in Hollywood, and some ideas of sending people there, like the next, place to live when the Earth isn't working out. Is there any reason why that could be possible, or is that just science fiction?
I think it's mostly science fiction, but I think it's so familiar when you look at it, right? If you imagine the landscapes, if you're there, other than the vegetation, it'd be like a very smoggy day, like Beijing or LA, and the sun would be kind of this blob in the sky. You wouldn't really see it. And you'd strip away the vegetation and you make it really cold. But if you look around you, you would not, it would be very familiar. And I think that familiarity is what's comforting almost to sci-fi writers, if you will. It'd be great. I mean, I can't imagine what Dragonfly is going to see as it's flying over the landscape. That's going to be spectacular. That first picture is going to be stunning. But I think maybe it's that. I would never.
You would never live there. Dragonfly, the helicopter, it's confirmed.
Yep.
Pretty much.
Got picked. Oh, I've completely lost time during this time. I think it was a year ago in July. It got picked.
Wow.
I'm wearing my shirt. Proud.
Yeah, it was a very interesting moment in the budgets, and NASA's education budget got maintained and increased. Europa Clipper got approved, and yeah, obviously Dragonfly too. So yeah,
it's a great time to study these ocean worlds. It's really kicking off.
That's really good. So we have 2 books to raffle today, and I love them. They were wrote by Bruce and Ana Luisa, and they are extremely amazing. They inspire you, even if you're not like into space or into as like astronomy or whatever, because they are from normal people from Costa Rica, and then they reached super cool like places and science positions at NASA. So today we'll have 2 of those. Yeah, Bruce has it there. I need my own book to get signed. So Bruce, I'm just leaving that comment there.
Too kind. Yeah, it's in English and Spanish, so you can practice both languages. The book's online too, and thanks to the Costa Rica Institute of Technology Publishing House, or the Editorial del Tecnológico de Costa Rica. Thanks a lot, guys, for always supporting us in these events. Yeah, it's a nice book for learning, basically about some of the Costa Ricans that made it to NASA, and it's already out of date because there are like 3 or 4 more. Thank goodness. But yeah, we're looking forward to the next edition. So yeah, check it out, and good luck to the raffle. Who's going to be in the raffle here?
So, give us the names. Who are the winners?
Well, the winners are, first is Dennis Murillo.
Dennis Murillo, you are the winner. Can you write me, or can you send me your email, please, so I can send you your book?
And the second one is Emily Marian Rojas. Those are the winners.
Winners, please send me an email. I want to send you these books. They're amazing, they're inspiring, and they are really funny and easy to read. So you will have a good thing to read before you sleep. So, thanks a lot, Sam. It was really, I'm extremely amazed. I really didn't know a lot about Titan. I can tell you, and I learned so much. So thank you. And I hope you can come to Costa Rica soon. We will be waiting for you here.
It was my pleasure. I would love to. It was a lot of fun. And Bruce, if people have questions after, feel free to forward them to me and I can answer them as best as I can.
Appreciate
it.
Yeah.
Just a quick question here. It says, where can I buy the book that has just been shown?
Oh, well, the Editorial the Tecnológico de Costa Rica, they will be able to provide that information. It's through Tech Costa Rica.
I just Googled the name and I bought it online. And it took me to the page of Tecnológico.
Yeah, we could send a link. Could you send that through maybe Danielle or someone there? It's all part of the same.
Yeah, it will be sent on the after mail that we send after every
okay, but thanks for asking, and I hope you enjoy the book.
So thanks a lot, everyone, for being here, to our amazing guest of tonight, and I hope we can still keep on dreaming of going to space and all these amazing things that we can have out there, and it inspires us every day.
Yeah, congratulations,
nice
Sam. Thanks very much.
Thank you. My pleasure. See you all.
Bye.
Bye.